So I'd like to welcome you to tonight's program. We're very glad you can join us. My name is Cynthia Blankenship. I'm the president of Geologists of Jackson Hole, and I also help run the speakers committee. And tonight, then, moving on tonight's program, we have another crowd favorite, Mike Adler. Mike graduated from MIT in 1971 with a PhD in solid state physics and worked at General Electric from 1971 until his retirement in 2000. He is widely published in the area of semiconductor physics with over 100 papers. And based on this, is a fellow of the Institute of Electrical and Electronics Engineers, or the IEEE, the world's largest professional society. Mike has been active in the IEEE for 30 years. He was on the board of directors from 1996 to 2004 and was the president in 2003. In retirement, Mike has been pursuing his hobbies of astronomy and photography, as well as traveling with his wife, Virginia. On the astronomy front, in 2014, he built an observatory at his Wilson, Wyoming home that houses 20-inch and 12.5-inch telescopes, along with his 6-inch refractor. He is a locally active volunteer, being vice president of Wyoming Stargazing and board member of the Friends of the Teton County Library, the Highland Park Homeowners Association, and the Geologists of Jackson Hole. Mike has been giving talks on a number of topics in astronomy, geology, climate change, and travel to groups in New York, the Royal Astronomy Society in Canada, and over 16 talks for the Geologists of Jackson Hole. Wow. He has spent countless hours leading the organization of 4 extended field trips for GJH to Scotland in 2015, Iceland in 17, New Zealand in 19, and Southwest Utah in 2022. So with that, let me welcome our tonight's speaker, Mike Adler.
Thank you very much, Cynthia, and thanks for everybody being here. And we're going to talk, as stated here, is we are all made of stardust, and so this is going to give you a little information as to how all that happened. Okay, now let's see here. Oops. Okay, this was advancing just fine earlier. Now it isn't. Escape. No. Technical problems. That's a problem. I wonder if I have to reboot this thing. Let's see if we get up to the top. Upper. We're hiding the menu. Okay, well, let's see what happened now. Let's see if it goes now. Okay, it's going now. Okay, whatever. We have this little distraction again. I wonder if I get rid of that, it's going to come back and it can be see hide floating money bar. You know, it doesn't like hiding the floating menu bar. What? It did, but it won't advance now that I've okay, I'll just leave it up. Maybe we could, well, okay. Okay, so in terms of the order of events, we're going to talk initially about the just an overview of star types, brightnesses, and distances, and then we're going to talk about star life cycles, specifically the sun, but then of a large star. And so we're going to talk about basically 2 types of stars mainly here. And then we move into the life cycles. After the life cycle, we'll talk about the elements, although that will be a theme kind of throughout the whole talk anyway. And then at the very end, we'll talk about the end states of stars, what happens when stars die. And that involves white dwarfs, neutron stars, and black holes. So moving on, just to calibrate you all in terms of what's out there, the universe contains something on the order of 10 to the 21st stars. That's probably an incomprehensible number to most of us. So if you think about the number of grains of sand that exist in the Earth, that's about how many stars there are. So a lot. It's also interesting, I heard a talk by Andy Grove of Intel, and he also points out that there's about that number of transistors in the chips that we have all in our computers all over the world. So that's also a fascinating little statistic you can put away. The Milky Way galaxy, which our solar system is a part of, is 100,000 light years in size and has about 200 billion stars. The nearest neighbor large galaxy is the Andromeda. It's got about 5 times that number of stars and is 2.5 million light years away. And just so you know, when you say light years, what that means is it's taken 2.5 million years for the light for the Andromeda galaxy to reach us that we can see, you know, through our telescopes. And actually, the Andromeda is somewhat visible to the naked eye. There's over 1 trillion galaxies in the universe, and just to give you an idea about our own little local solar system, Pluto, which is no longer a planet, but it's 5.4 billion kilometers away. Now, but that's only 5 light hours, not years, hours. And it took the satellite that took the pictures of Pluto 9 years to get there, so a long way. And so our nearest neighbor star is 4.3 light years away. And just to calibrate you on that is if the sun and the earth were only a foot apart, that star would be 87,500 miles away. So that's a long way away. And I answer lots of questions on Quora about, and the people say, well, when are we going to get onto a rocket ship and go see our nearest neighbor star? And the answer is no time soon. Because that spacecraft, the Voyager spacecraft, which is traveling around 30,000 miles an hour, 60,000 kilometers, would take 60,000 years to get there. That's the nearest star other than the sun. So intergalactic space travel, you'll have to put that off for now. Okay, so getting back to the star story, we're going to be talking about 2 classes of stars. From the brightest and the largest on this chart, there's 7 different classes, and they range from what they call O stars on the left, O class stars, and on the right, this G star. The G happens to be the size of the sun. So that's the difference in sizes. So the radius of the large star on the left is 10 times that of the sun. Its luminosity is 100,000 times brighter because it's a combination of the fact that its surface temperature is 40,000 degrees K versus 6,000 degrees K for the sun, plus the fact it's huge. So it has more surface area. It emits a lot more light. So what does that get you, or what it doesn't get you, is a long life. So the sun will last about 10 billion years. This star will last 10 million years. So it has so large stars don't live long is the bottom line, and small stars, a star a tenth of the size of the sun, will live a 10 trillion years, essentially forever. Yeah. Oh, okay. Let's see. Floating menu. Well, okay. So I have to stop the share for a second. I'll go up here and do the video. Okay. All right. Okay. All right. So moving on. Okay. Messing with this floating menu bar is a. Okay, here we go. Okay, well, I went the wrong direction. All right, so what we're going to talk about now are stellar life cycles, and this chart kind of gives you the idea. We're talking about basically 2 classes. One is a medium-sized star, and another is a star 10 times the size of the sun. And all stars begin the same way. They come from a cloud of gas and dust, which some event causes that gas and dust to get squeezed, and eventually gravity takes over and heats it up. And by the time, if you get to 10 million degrees Kelvin, you get a live star. Anyway, the star lives on the left side here, the medium-sized star, the sun ball here. It lives for about almost the full life size in that regime. But then it becomes what's called a red giant. The hydrogen runs out of the core. It starts burning helium in the core, which is the product of the hydrogen reaction. And it also that triggers burning of the shell. There's hydrogen in the shell. It makes the star increase in size 100 times. And that has nasty consequences for our solar system, by the way. We'll get to that. And then, but that phase doesn't last long. The same thing happens for the large stars too, except the timescales are totally different. The red giant then runs out of fuel again, totally out of fuel. It creates a good half of it disappears as a planetary nebula, essentially in the sky, and it ends up as a white dwarf, which is 100 times smaller than the original star. So it's and we'll talk more about that as we go on. About early in the 20th century, people realized that there was a way to characterize stars. And this chart is called an HR diagram. And on the vertical axis is brightness. It's all logarithmic. And on the horizontal axis is the actual surface temperatures going from 30,000 degrees to 6,000 here, and then to 3,000 for the smallest stars. And this band here in the middle is called the main sequence. And any star in the main, and 90% of the stars are in the main sequence. So what you can do very nicely is you can measure with a spectrometer the color of the star. And once you know the color of the star, you look down at this lower level and you see, well, if it happened to be this orange, yellowish color like our sun is, you go up to the main sequence, and that tells you what the size of the star is. Needless to say, one solar is all calibrated by the sun. One solar radius, and it tells you what the life is, 10 billion years, it says here. And then it also gives you the mass. But now let's go to the O star. So if you realize that you now have an O star, and you can't tell it because they all look the same size, but because they're so far away. But if you look at the O star and then run all the way up, you find, sure enough, it lives 10 million years. It has 10 solar radii, and its mass is 10 times the sun. And that's all on this one chart. So it's kind of cool. Okay, so in terms of, I mentioned earlier how stars get formed. And stars begin to form when this cloud of gas and dust coalesces and makes a star. And then the sun is well past that stage, needless to say. And so here's a graph or a diagram that shows the age of the sun. Here we are right now at this point called now. And it was just 4.5 billion years after the solar system and the sun were formed all at the same time. What's been happening over this period of 4.5 billion years and will continue for the next 4 billion years is the sun is gradually getting warmer. It's getting bigger and it's getting warmer. That's not good news for anyone if we somehow survive that long on the Earth either, by the way. Then it becomes this red giant, which occurs when the hydrogen in the core runs out. There's what they call the ash of this nuclear reaction is helium. The helium starts another nuclear reaction, turning it into carbon. But the hydrogen in the outer part of the star begins to burn. That is, it forms, it goes on in its own nuclear reaction. That causes the star to expand 100 times more. And that's the red giant phase. But that doesn't last very long, 50 million years. That's a long time by our standards, but by 10 billion years, that's not a long time. It then disappears. The outer area of the stars run out of fuel. It just sort of moves out and creates this planetary nebula, and then eventually a white dwarf, which I mentioned earlier is very small. The reactions that create the burning, when the astronomers talk about burning hydrogen, what they're talking about is a nuclear fusion reaction, which takes 2 hydrogen atoms, and in this case, it's deuterium and tritium with different amounts of nucleus, creates helium. And so why is that why is that important? It's important because the helium product of this nuclear fusion reaction has 0.7% less mass. And why is that important? Well, that 0.7 of a less mass results in all the light and energy that the sun produces. And that's E equals mc squared. So if you translate that 0.7% less mass, you get a lot of energy. The sun produces 4.2526 million tons of mass every second, and it turns it into this whopping amount of energy, which is a very large number, 3.8 times 10 to the 26 watts. But yeah, if someone did the math and says that's equivalent to 92 billion megatons per second of TNT every second. So that 0.7% different mass creates a lot of energy. That's because there's a C after the mass, it's C squared. So that's Einstein, so there you go. So that's why the sun that's what causes the light and the heat from the sun. So looking at the cross section of the sun is a medium-sized star, life of about 10 billion years, and we're halfway through it. It has 6 layers, starting with a core, and a radiative zone, a convective zone, a surface, and then a chromosphere right around the surface, and then a corona. The core temperature is almost 16 million degrees Kelvin, which supports that nuclear reaction. And the surface of the sun is about 6,000 degrees Kelvin. And the corona, interestingly enough, is over 1 million degrees, maybe 1 to 2 million degrees. And the sun is composed mainly of hydrogen. That's what that's the primordial elements in after the Big Bang were 2. One is hydrogen and one is helium. They were already created before any stars. But stars basically, as you can see from the description, all stars start out burning hydrogen. But they have trace. Now the sun, because the sun is a 3rd generation star, it has trace elements that resulted from other stars that existed prior to the sun. And that's why we have all these elements, and they're in the sun, they're in all the planets, they're in the solar system. 2% of the sun is oxygen, carbon, iron, and then lesser amounts of the heavier elements. The sun is 100 times the size of the Earth. So this is a picture I took a little while ago with one of my telescopes, solar telescope, of the surface of the sun, and you can see all the amazing amounts of structure on there. There's a couple of black holes, not black holes. There's a couple of dark areas on the surface, which are slightly colored sunspots. You can see the patterns. There's a storm going on here, and then there's also because we're looking at the profile here, you're seeing this prominence. There are prominences right above this too, but we're looking right at them, so you don't see them. Okay, so here's a picture that just tells you roughly, just graphically, the size of the sun compared to the planets in the solar system. So how does the heat that the sun produces in the core get to the surface? And well, so you have this core. It's at 50 million degrees K. It produces the energy. The energy is released as high energy gamma rays. These gamma rays propagate through the radiation zone. They get absorbed, re-emitted. Finally, they reach the energy reaches the next layer, which is the convection zone, 0.7 of the radii out. The heat travels through there by convection, and then finally reaches the surface, which is the photosphere. That's the surface we can see. And that surface is 5,800 degrees. You can read the numbers, 300. It's relative to the size of the sun. It's quite thin. So that temperature is what determines the light and heat we get from the sun. It's called, the radiation is called black body radiation. If you heat any object up uniformly, it will emit light. it's called black body, even though it's not black, but so that's where the heat and sun energy from the sun comes from, that surface, not from, and the surface is heated by the reaction inside. But the photons, one of the things that people don't understand, a lot of people don't understand, is the photons from the middle of that are generated in the middle of the sun are not the photons that you see, that we are. Good thing they aren't, because those are gamma rays that kill you. It's the wavelength of the light that we get is all due to the surface temperature of the sun, and so that's and black body radiation. Everybody's done it, has had an example of that. If you heat up a piece of metal and it glows red, that's black body radiation. That's so it happens. We all see it. It just never relates to it. Okay, so this is the curve this is the irradiance in units that isn't important as a function of wavelength for the radiation from the sun. And the yellow curve here is an ideal black body surface radiation, and it shows that and it's very nice for us, of course, is that it happens to peak out almost in the visible wavelengths there, but it also emits in the ultraviolet. We have to put sunscreen on because of that, and it also emits in the infrared, which also produces heat. The actual sun, the actual radiation that gets to the surface or above our atmosphere is somewhat more jagged, because stuff is going on in the sun surface that causes some of the radiation to be absorbed, and also our own I guess I've gone in the wrong direction again. And our own atmosphere takes chunks of it out, and that's what's. So the curve, the last curve, the lower curve, is the irradiance that arrives at the Earth's surface, and as you can see, a lot of it's visible. Okay, then corona is the outer atmosphere of the sun. It extends 15 radii, solar radii, or 6.5 million miles from the sun. It creates the solar wind, comes from the corona. The average temperature is extremely high. It's well over the surface of the sun. The surface is 6,000 degrees. The temperature of the corona is 1,000,000 degrees, and so that's a duh. How does that happen? Well, I'm not going to go into it in detail, but I have my previous talk I did, but it comes from the magnetic energy in the sun being essentially transferred to the corona, and that magnetic energy heats up the corona to its high temperatures. The sun emits about 1,000,000 tons of charged particles every day, or excuse me, every second, and that's the solar wind that the sun generates. And the solar wind is what is responsible. These charged particles are what's responsible for aurora here on Earth. Okay, so moving on in terms of the evolution of the sun. So in this next period of time beyond where we are now, the sun is going to gradually get bigger. It's going to get hotter, and that's in this that's in this lower. Where we are here is on this lower plot. We're right here, but it's going to continue this warming trend for actually another 5 billion years. But then it runs out of hydrogen, as I said. Helium starts burning in the core. Hydrogen starts burning in the outer parts of the sun. It expands 100x, becomes 100 times more luminous than it was. That lasts for about 50,000 years, 50 million years, excuse me. And then it runs out of that fuel, so the sun basically stops producing heat. The outer part of the sun floats away as a nebula, and the inner part becomes, which is about half the mass of the sun, becomes concentrated in the size of the Earth, half the mass. So it's extremely dense. But just to give you a little flavor of what's coming attractions as far as our sun goes nearer in, this is a plot of just a plot of various things, but one is the sun today. It relates to the sun today, and then larger and smaller numbers. This is time from the I be careful touching the screen. This then on the horizontal axis is time and so we're right now we're here at 0, which is 4.5 billion years from when the sun was created, and it shows what's going to happen in the next 3 billion years. And you can see this. The graph shows the luminosity. That's the light is increasing. The radius is increasing. The temperature of the surface is about the same. And there's this little spot right here, which is about 1 billion years from now. It says runaway greenhouse on Earth. What that means is the sun is going to get so hot that it's actually going to boil away all the water on the surface of the Earth. So you won't want to be here at that time. We won't be, by the way, because even before that, it's going to get so hot that it won't be habitable on the planet. So regardless of global warming, the sun itself is going to provide the last word on that subject. So anyway, it's yeah, it's a little disquieting to know that our world here will not last into infinity in terms of a habitable place. Anyway, it is what it is. Okay, and just to Cynthia was asking me whether we talk about this. Yes, we are, and here we are talking about it. So here's the top graph on this plot is the current situation, the current sun radius, inside the Mercury orbit, Venus, Earth, etc., the habitable zone right where we are on the Earth. Here's what happens when the sun becomes a red giant in 5 billion years. It's projected that it will probably encompass the orbit of Venus. So it gets that big. Again, needless to say, it's going to be pretty toasty on Earth too. And in fact, it could conceivably be within the Earth's orbit too, but the analysis suggests maybe not quite. So what happens is it gets really hot here, and the habitable zone moves out to Jupiter and Saturn. So maybe if people are still around and they could figure out a way to live on the moons of these planets, they will be in the habitable zone. Okay, then we talked about the next transition, which is the red giant stops up and dies because of the hydrogen fuel is used up, helium fuel is used up, and it now blows off the upper layer. I should mention that you'll see this when we talked about larger stars. The helium that's in the core of the sun will never get hot enough to actually start another nuclear reaction. It has to reach 600 million degrees before helium can fuse into carbon. It's not going to happen. The sun isn't big enough to produce heat like that. So it's not going to happen. And it enters this phase where the outer areas leave and it becomes a white dwarf, like shown in here, which is, a 100th of the size. And the outer layers expand and create a nebula. And the white dwarf is very dense. It's about half the mass of the sun in an air volume about the size of the Earth. And it's as dense as electrons can get. So what keeps it from getting smaller is electron degeneracy. Electrons can't be in the same place. 2 electrons can't be in the same place. So that keeps the sun from getting any smaller than that. But it's still pretty darn small. And the density works out to be 1 ton per cubic centimeter. So essentially a teaspoonful of what this white dwarf weighs a ton. If you can, to get ready for what happens with a neutron star, boy, this is nothing. But anyway, the surface temperature of the white dwarf will be initially pretty warm, 20,000 to 30,000 K, but it's going to be about 1/30th of the luminosity of the current sun. And why is that with this high surface temperature? Because it's tiny. And so it doesn't have much surface to radiate. So even though it's very hot, it doesn't produce overall much heat. And so here's an interesting point. It's again a Quora question I answered a while ago. Someone asked, well, when the sun becomes a white dwarf, will it support life? Well, if somehow the Earth survives the red giant phase, because remember, it's gone through the red giant phase by the time it gets to the white dwarf, it's got to be really toasty. And so now you have a sun, or what's left of it is produced 1/30th of the light. It's going to be really cold here, so we're going to go from temperatures off the scale on the high side to minus 147 C on the and so it's nothing in the solar system will produce life at that point. Because there isn't going to be enough heat for not even for the Earth. And in fact, I worked out the math. I think even Mercury won't be warm enough to be habitable. Okay, so the end of the life of the sun, I've pretty much described it. It goes from where we are up to the red giant, and this is this HR diagram, another version of it, but it follows this path. So it was on the main sequence, it moves up, up, and becomes much bigger, and then becomes a planetary nebula, is kicked off, and then it falls down to a white dwarf. And the white dwarf will eventually cool off because it's not producing any heat. It's gradually going to get cool. Over 10 trillion years, it'll be what's called a black dwarf. It won't be white anymore. This is an example of what one of these nebula look like. They call them planetary nebula, but they have nothing to do with planets. They just happen to be round. And the earlier astronomers had no idea what they were, so they called them planetary. But and this is something called M57, which is a ring nebula. You can see it with a small telescope right here in Jackson if you look for it. This is just an example, though. This graph here, this shows a picture of a star cluster, and this was, someone worked this out. They looked at each of the stars in the star cluster and figured out what its temperature was and what its luminosity was, and they plotted it. And guess what? So this is actually data from all these stars in this star cluster, actually tracing out the path that I just showed you over here. So this is not, these are not mirrors. This actually happens. This is real life. This is what actually happens. So the astronomers pretty well figured this out. Okay, this is a picture of that same planetary nebula M57 that I made from from Webb data. I had that in my exhibit here last year. And this is the same picture, but here's a version of it I took with my own telescope right here in Jackson. It's not quite as nice, but it's not too bad either. And this is the picture that was at the front end of the talk is of the Helix Nebula, sometimes referred to as the Eye of God. It's also another planetary nebula. And the little dot in the middle of this, is the sun. And this is the cloud, the nebula around it that was leftover material that didn't get in the white dwarf. And this is located about 650 light years away, which is actually quite close. So now we're going to shift to big stars. And so we went through the story with the little stars or the sun. The big star pretty much has a similar beginning, except everything's bigger and shorter. So the long phase of this star is only 10 million years. It then becomes, for the same reason as I described for the sun, it grows up into a giant, supergiant, red-blue giant. And in that phase, it'll last only about, instead of 10 million years, it'll last 1 million year. It will run out of fuel. Well, it doesn't, in this case, it doesn't run out of fuel. Something different happens. During the process of this red giant phase here, this guy, it'll produce elements all the way out to iron. In other words, what happens is, remember I said when the carbon in the core of the sun never gets hot enough, 600 million K, to start a reaction that'll make it turn it into oxygen. Well, in a big star, it does. And then the oxygen burns, and then it creates the next element, and then the next element. And this goes all the way out to iron, and it'll finally create iron. And at that point, all hell breaks loose. I'll tell you why. A supernova explosion, and the end result is either, so instead of quietly dying, a large star doesn't go away quietly, it explodes. and it creates either a pulsar or a neutron star or a black hole. And so this is just a little cartoon. Actually, I made this one myself, but so we have this hydrogen burning phase that lasts 10 million years. We have this red giant phase lasting 1 million years. But the difference is, and that's what's on the right side of this view graph, the carbon will burn for 1,000 years. It will actually fuse, and it'll create oxygen. And then oxygen, it'll leave a residue of oxygen, it leaves a residue of carbon. The oxygen burns for 1 year. Neon and manganese burns for 6 months. Silicon burns for about 1 day. Iron core lasts a fraction of a second. And so the question is, why is that iron core lasting a fraction of a second? Well, that's where it gets exciting, because, well, anyway, this is just the various nuclear reactions that occur. And I won't take the time to go through these, but it's proton to proton, triple alpha process, and all of these are different nuclear processes that are in play. So, as I sort of preempted myself, so the carbon gets starts this process and works itself along. Carbon burns itself out, creates oxygen. The oxygen just burns itself out, creates the next element. It goes all the way out to and in fact, the ultimate temperature in this core is 10 million. It reaches well, it starts at 10 million and it gets to 1 billion degrees, and creates all these elements in the process. Okay, so once the last phase of element producing in the core of these large stars is silicon, and silicon will burn and create iron, and it does. And this phase lasts less than a day. You know, thinking about a star that has existed for 10 million years, the last phase of it is producing these elements, but you can see the time that each element it takes to produce the next element gets shorter and shorter and shorter and shorter. Finally, this last one is silicon, and it creates iron. Then what happens? Well, iron will not enter another fusion reaction, because it has the highest binding energy of any nucleus, and it becomes endothermic. It requires additional energy to form higher elements, and that's the rub. There's no additional energy. So what happens? Well, the core shrinks because now no heat is being produced by the core. Gravity starts squeezing. And in the past, gravity would squeeze and create the next element. Another fusion reaction would happen. Well, it's not going to happen now with iron. It takes extra energy. Squeezes and squeezes. Neutrinos get spit out all over the place. And the net result is it gets so hot that electrons and protons actually merge to become neutrons. And the core becomes as dense as an atomic nucleus. Because of that huge amount of density, and in such a small space, regions around the core plunge into the middle of the core at 15% of the speed of light, really fast. So all this is happening in a blink. And the result is that there's a huge rebound reaction that occurs. These outer layers are crashing in. They're hitting this rock, the super dense core. It rebounds out and creates what's called a supernova. The star just explodes. And this diagram is just a cartoon that shows the infall, then the rebound, and the reaction. This little graph here gives you an idea of the time. A lot goes on in the first 15 seconds of this reaction, but the light from one of these reactions from the supernova doesn't go away immediately. It'll last actually a number of days, maybe some of them. The green curve, the red curve is the curve for this type of supernova. There's a couple of different types. Okay, so the remnant of the star, what's left of it, becomes either a neutron star or a black hole. This is a picture I took. No, I didn't take this picture. I made this picture. I made it from a combination of data from Webb and the Hubble. And this is the Crab Nebula. It was when supernova actually seen in 1054. And I mentioned it was a joint picture that I made myself out of the data. It resulted in a neutron star pulsar. And this is I expanded this to show you the detail. So the neutron star, a lot of the neutron stars don't actually emit in the emit light in the visible, but this one does, and so you can see it. So that star right where the air, that line is, but there it is. These are shock waves that from this. So this is all a result of this supernova. These are shock waves from the supernova that occurred, and all the nebula around it is stuff from the supernova that made this beautiful nebula, actually. And then there's what they call synchrotron radiation, which is electrons are orbiting around this star and because of the huge magnetic field that the neutron star provides, and it emits light, and that's what this outer band of light is. And this is the only video I'm going to show. This was taken. It's actually a set of pictures stills put together to make it look like a video. But this is actually showing the center of that object, and the blue is from is X-ray radiation taken by the Chandra Space Telescope, and the red is from the Hubble. And this video is really short. In fact, I'll probably run it a couple of times because it's so short. But you can see it. It's actually spinning. It spins at a 30th of a second. The object, this pulsar, is spinning, and it's spitting out light and particles while it's doing this. Well, that's why it's called a pulsar. Not every neutron star does this, but this one does, and this is a very famous one in the Crab Nebula. And there it is again. Okay, so this is another supernova remnant that was I took right here in River City. This is called the Veil Nebula, and this was from a supernova that occurred something like 10 to 20,000 years ago. And it's still evolving. So these are all relatively recent things, the creation. So now we're going to talk about, we've talked about how the elements up to iron get created. They get created in the core of the large stars and also in the core of the little star, like the sun. But the sun only produces little more. Remember, helium was produced during the Big Bang, but the hydrogen reaction also produces helium. So a little more helium gets produced, carbon gets produced, but that's it for the sun. At least there's another story here. We'll get back to that. And the bigger stars produce elements all the way out in the core by fusion, all the way out to iron. And that's kind of what you're seeing here. But then there's all the rest of the stuff. So where does that come from? So that's what we're going to talk about now. So elements higher than iron, atomic number 26, are only created by processes other than fusion in the star's core. Other than fusion, not fusion. You only get out to iron through fusion. And you notice that there's a lot of iron because it's a natural place, so there's a great deal of it produced. So creating the elements. So I mentioned this already, but the hydrogen and helium were primordial. They were created in the Big Bang. Heavier elements are created by some other process, which we're going to talk about. The elements, these particular elements beyond iron, you can see this is a logarithmic scale on the left side. You can see that the number of elements on the left side is right here are way less than the elements produced in the star's core. Here's the periodic table. And now we're going to spend the next 2 hours talking about this. No, I'm going to, this is a periodic table that's been modified to show where the elements come from. And I'll give you, we just recap some of the things I just said. Hydrogen, this light green color, hydrogen helium on the left and the right side came from Big Bang nuclear during the Big Bang. You'll notice that then the next color is low mass stars, dying low mass stars. That's this sort of light color, yellow, orange. And a little helium is produced by it, and you can see carbon and maybe a little nitrogen. I didn't get into that detail of why nitrogen is produced, but apparently some of it is by the low mass stars in the cores. Then the darker, then you'll also notice, and I'll get back to this, you'll also notice, which is, at first, and it just surprised me too, look at all the light colored orange in these heavier elements. How did this happen? So light colored, I think you were building up to the idea that the big stars produce the heavier elements. Not totally true. It's true they do, but the little stars actually do too. So how? We'll get to that. Okay, so then there's the exploding big stars. That is the stars 10 times or bigger than the sun. That's this darker orange. And you can see it produced, and so the elements that have two colors mean that they're produced by more than one process. But they're produced all the way out to iron here. But you can see it goes much beyond that. And this dark orange goes way out. So it's producing, these large stars are producing elements that have a higher atomic number than iron. Then you'll see this gray color here, lots of this. This is a real recent development in terms of understanding how elements are created. And these are as a result of what we now think, or scientists think, not me, I'm not into this field, but that are mergers of neutron stars, and a neutron star merger can also produce heavy elements. And we now think that the heaviest elements, and most of the heaviest elements, and they are produced by these neutron stars. But notice also the light orange. These lighter stars are producing elements quite a ways, way, way, way out. Bigger than the bigger stars. Notice they go away. But okay, so let's go into this. So there's two processes that make these stars beyond iron. One is called the S process, and one is called the R process. And I'm not going to bore you with going through this, but you can see the R process, which is called the fast neutron process, produces most of the heavy, like iron, like gold here, platinum, and this S process, the lighter green, produces mostly somewhat lighter elements. So what's going on? Okay, the R process is called the rapid neutron capture process. It creates some of the heavier elements. It was thought until semi-recently that the R process only occurred during supernova. But that's no longer thought to be the case. I mean, it is produced during the supernova, but it's not the only case. Neutron star mergers were proposed as early as 1970, but there was no data that would suggest that it could happen. But then in 2017, with LIGO, the gravity wave detectors, they detected neutron star mergers. They knew they actually happened. And now, and the previous data, the previous analysis said when they do merge, they're going to produce some of the heaviest elements. Well, guess what? They do happen. They do merge based on what we just found out from LIGO. And so now this is actually an area of active research. This is not a done deal. It's pretty much the case. One of the issues here was, are there enough of these neutron star mergers to account for all these heavy elements? And the R process occurs very rapidly in the first few seconds of the event. What happens during, like, the supernova, the neutrons crash into the nucleus so fast that they build up into heavier elements before they can naturally radioactively decay. And this process happens very quickly in the first 15 seconds of a supernova, for example. And about half of the atomic nuclei, other than iron, beyond iron, are produced by the R process. And it's thought it's between the neutron mergers and the supernovas. And so I just refer you back to this chart. So now that we just talked about this, you can see the darker orange, what is produced by the mostly by the supernovas, and then the gray by the neutron star mergers based on this recent understanding that neutron mergers do occur. Okay, so then we have to talk about the S process, and this is quite interesting. The S process is called the slow neutron. That was the fast neutron. This is the slow neutron. This is a process where stars capture additional neutrons to form a nucleus with higher atomic number, and the process is slow, taking thousands of years, maybe millions of years, with extended time between captures, and it only occurs in the red giant phase of medium-sized stars. And the reason is that the merger takes so long, and the red giant, super red giants of these large stars only live for less than 1 million years. That's not long enough to produce many of these elements. But the 50 million years for these smaller stars is long enough. And so that's how a great deal of these other elements are produced. They are produced slowly by gradually merging neutrons with the existing nuclei and adding neutron after neutron after neutron, which then, of course, can break into a hydrogen atom and a electron, creating the heaviest of the stars. So, as I said, it only happens in the low to medium stars because the red giants, the big ones, don't last long enough for it to happen. And this actually accounts for about half of the atomic nuclei heavier than iron, this process. Kind of interesting. And there it is. I just show it. And so one last time. Okay, so the event summary. Hydrogen and helium are primordial after the Big Bang. Everything else happens from stellar nuclear synthesis, one way or the other. Stars evolve because gravity causes these non-burning stellar core to contract and heat up and contract and heat up, and one after the other, this onion peel thing gradually builds up, and you get stars all the way out. You get elements all the way out to hydrogen, iron that way. Then you get higher elements, higher mass elements are produced by these two other processes, R and S processes. And it's kind of, I find this kind of interesting, just the statistics here, taking the case just of the large star as an example. So here's a large star that lives over 10 million years. It creates helium for 1 million years, carbon for 1,000, oxygen for 1 year, silicon for 1 day, iron for less than a second. And then it explodes, creating all these other elements in the next 15 seconds. And so what's amazing is we used to thinking of stars as lasting forever, and they don't. And a star like a large star actually produces all of this in times that are even short by our time scales, in seconds and fractions of a second. So I find that, and this diagram here is just this kind of the onion peel diagram showing that these layers of elements that are produced in the large stars. Okay, so a last little snippet here, talking about that's sort of the end of the story as far as how stars are created or how elements are created. But I thought I'd throw in a few graphs on neutron stars and black holes. So this guy, John Wheeler, produced this graph in 1965. He actually he's a famous scientist, and he coined the phrase black hole. So he was the first one that came. But so what he developed this diagram, because the question is when a large star, what determines whether it becomes a black hole or a neutron star? And he developed this, or for example, a white dwarf. So here we have mass on the left axis, and we have the circumference in kilometers across the horizontal axis. And so here on the very right side, we have the sun. And the sun, when it follow to the left, it hits this curve here, which says white dwarfs. You probably can't see it, but it says white dwarfs. So the sun produces a white dwarf. If you go up in mass, and this is the mass not of the total sun, it's the mass of the core after is blown off the outer layers. So once you get above about 1.5 solar masses, it no longer results in a white dwarf, and you get a neutron star. And the Procyon is an example of one, and that gets over to here. And then if the mass of the core star is like 3 or over 2 stellar masses, you get a black hole. And an example of that is the star Sirius, which we see as a dog star in the night sky in the winter. That one is destined to become a black hole. Betelgeuse in the Orion constellation is destined to become a black hole, because it will have enough mass that even I guess I didn't really mention that. We talked about the electron degeneracy. The thing that keeps the core of the neutron star what it is, it can't get it can get smaller. It can become a black hole. But before it does that, it is limited by what's called neutron degeneracy. How close can you actually pack neutrons? And that's what it's called. But at some point, a star can start out to become a neutron star, but then cascade down into a black hole. So that can also happen. Yeah, and so anyway, we talked about this. A neutron star is a dense stellar corpse of closely packed degenerate neutrons. That's what it means, is as close as you can pack a neutron together. You can pack neutrons a lot more densely than you can pack electrons. In fact, wrong direction. A teaspoon, okay, so a teaspoon of a neutron star is pretty amazing. It weighs 1 billion tons, whereas a teaspoon of a white dwarf is only 1 ton. So 10 million times more, 10 to the 9th more density in a neutron star than in the white dwarf. But the white dwarf isn't exactly shabby either in terms of its density. It has a huge magnetic field, and rotates, and when it rotates, it can produce these pulses that we can see. In fact, neutron stars, the rotation of a neutron star is extremely stable, and in fact is so stable that it actually is more stable than even atomic clocks. That period is extremely reproducible and stable. And when the beams are directed to us, that's a pulsar. You get this rotation, and if it's angled just right, you get a periodic wave of light that comes from these things. And the neutron star is it has its own structure to it, and the lower diagram here just shows that these things do rotate, and they spit out material, light. And if you're pointed in the right direction, it's like a lighthouse. So the last thing here is black holes. So all matter distorts space, but and time, but the most extreme are black holes. And so most of you have heard, probably seen diagrams like this. This is a distortion of space by a black hole. There's something called an event horizon, which I'll mention in a second, and within the event, the distortion of space gets even more extreme, potentially ending up as a singularity. In fact, as you probably know from previous information, any object that gets close to that event horizon can get sucked in, and there's no return, including light. Light gets bent so severely inside the event horizon that it can't escape. Hence, that's the name for the black hole, because light cannot escape from it. Anything inside cannot. Einstein, the theory of all of this comes from Einstein. He himself, though, never believed that it could happen, but his theory predicted it. And in fact, and this is all relatively recent, in the last 40 years, that people realize these things do exist. Okay, and yeah, and if you want to talk about what it would be like to enter one of these things, a large black hole, even a person going across the event horizon would not immediately know there was a problem. A small black hole, you would notice immediately, because what happens is the gravity gets stronger very fast as you get closer to the singularity. And just like what happens with tidal effects, where the ocean gets pulled due to the difference in gravity from the moon as a function of distance, it gets pulled apart. Well, this would get pulled apart, and you would rip apart anything that would fall into the black hole. Eventually, it would get totally spaghettied. So this diagram just talks about several aspects of the black hole, one of which is the innermost stable orbit. So this is the closest orbit you can be at a black hole without spiraling into it. And for a non-rotating black hole, it's about 3 times the radius of the event horizon. For a space is rapidly distorted near a black hole, as we just showed, but time also is. And time slows near a black hole, so that by the time it passes almost at a zero rate at the event horizon. So it's time. You probably know that higher gravity causes clocks to run slower, time to run slower. Well, at the intense gravity of a black hole, it almost stops. And if you were out there in a spaceship and you watched something get sucked into the black hole, you would never see it happen. It would gradually, that object would gradually move, and it would seem to be moving slower and slower and slower. Finally, it would disappear, partly because light becomes redshifted and you wouldn't see it anyway, but it would slow down and totally disappear. Outside of the black hole, there's other aspects to it. For example, there's this accretion disk. If this is a black hole, why is this here? And so this is material that has been accumulated by the black hole that's spinning around it, and might be spinning fast enough, because there's nothing magic about gravity. The gravity of a black hole, objects can rotate around the black hole. Because it's mass. It's a lot of mass, but it's mass. So objects can rotate stably. But if they're rotating less than the speed necessary to keep it on a stable orbit, it'll gradually get sucked in and closer and closer and closer until it finally falls in. And then there's something called the photon sphere. Light also gets trapped and it creates circles around the black hole. And then there's then the energy of this accretion disk rotating around. Plus, most black holes are actually rotating themselves. That all creates what is called a relativistic jet, this jet that becomes above and below the black hole. And again, these are light that's produced by the black hole, but it's not. But this is all external to the black hole. It's not inside. And interestingly enough, and this is, I think, the last point, black holes are not completely black either. They emit some light, and this is called Hawking radiation. Now, the amount of light that they emit is extremely little. And for a black hole with the mass of the sun, it's estimated that it will live to something like 10 to the 67th years. So and in fact, in people thinking about the ultimate end of the universe, the last things that would likely go will be black holes, because they live so long. And so this is sort of the last chart. You are made of stardust, and 65% of that is oxygen, 18.5 carbon, 9.5 hydrogen, 3.2 nitrogen, et cetera, and beyond. Yeah, I have a few more charts. This is another image of a planetary nebula that's visible in the northern sky, and a couple of pictures that I just did from Webb. So anyway, that's the story.
All right, so I've asked the questions on chat, but I don't have any yet. So if we have any questions in the audience, do that.
Yeah. Okay, Bob.
The cycle from star to black hole, it depended on some relatively random value.
Mhm.
Size of the star, star growth, mass of the star.
Right, sure.
So, can't say for sure. We don't go through any of these things. It's all random.
Well, it's not totally random, but it does depend on, I'm sure fine structure associated with it, but in the broad sense, these numbers about the mass certain above a certain mass level will probably be a black hole versus a neutron, probably, but it's not a guaranteed thing. Yeah, there is no, as you said, the physics of all of this is very complicated, and these the thing that that diagram showed was a rough estimate of where these dividing lines are.
So the transition from a star-like structure to a black hole or something like that is dependent on these variables. And there's nothing that triggers it. You can't trigger the formation of a black hole.
Well, it does. The
So
process is.
Thanks, can you?
Yeah. So let me
I have another question.
let me just say the question. One way to pose the question is what triggers the creation of a black hole or a neutron star, for that matter, and it's the end of the star reaching iron.
Yeah.
That's what triggers it, because iron is unstable at that point. It's not producing enough heat anymore, and it collapses, and that creates the end of the star, and that creates a supernova, which then results in one of the other two things happening, either a neutron star or a black hole being created. So the star itself will not survive this. There's no third possibility, but exactly which one it is and is not preordained. Yeah. Oh, way back. Okay. Yeah.
Like answer. How do we know for certain that we're not in a black hole and that time has already been slowed down?
Yeah. Yeah. There's a question I'm not going to be able to answer, by the way, but the question was, how do we know that we ourselves are not in a black hole? And the only thing you could say about that is that black holes are not that big. The radius of, I didn't mention this, but the radius of a black hole that's, say, 100 solar masses is no, in fact, it might, it's solar masses. So yes, it could, Earth could fit into almost, but not, there can be really small black holes too, but there can be bigger ones, and the bigger ones will be large enough. But what you notice, what an element of being in a black hole is an extremely strong gravitational gradient. In other words, the strength of the gravity is the center of the black hole is a singularity, which once physics finally figures out how to deal with quantum gravity, we'll understand what happens so no one knows about the singularity, what goes on in the singularity, but it's really going to be a tiny area, and the gravity is going to change dramatically as you approach it. So now you have to say, probably on the scale of our, the distance between us and the sun, that would be enough distance that even a huge black hole would have a huge gravitational gradient. We don't have it. I mean, it's not there. But that would be the real thing that would tell you, all right, could you be in a black hole? Well, you would have to find, and in fact, almost in a smaller black hole, matter just gets ripped apart almost immediately because of the tidal effects, they call it, but it's the difference in gravity as you change distance. Yeah. Yeah.
This was really interesting, by the way. I'm trying to picture what happens when a star is triggered into the burning phase.
Yeah.
I'm picturing a lot of hydrogen, and the helium just drifts in.
No.
Or is it pushed in?
No. It's made by the star. The hydrogen, that's the whole point of how say the sun works, is creating helium in the nuclear fusion reaction in the core of the star, of the sun, say, is two hydrogens create a nucleus create helium. This helium isn't drifting in, it's being actually created. So, and all by the nuclear fusion. And when we talk about the big stars, that's what's going, every element that's happening is being created by the fusion process of the previous. So like carbon is being squeezed by 60 million degrees, 600 million degrees. At that temperature, carbon will fuse together and create an oxygen. So the oxygen isn't flowing into it; it's being created. Yeah. Well, you know, we're talking about yeah. Well, but that's what people are trying to do on this planet. We're trying to create fusion reactors. And what we're trying to do is take hydrogen and make helium. Because if you can make helium, you're going to have this 0.7% extra energy, and that's a lot. It turns out there's those c squares after the mass that you know, that's the speed of light squared. That's a lot. Turns out it's a ton of energy. So that's why fusion. That's why there's the holy grail is to create a fusion reactor.
We have a question from chat. What are thought to be the causes for solar wind to accelerate?
Yeah. What are the causes for solar wind to accelerate? And it's gravity. So it all depends on the gravitational field that the wind is entering. And in fact, the solar wind from the sun is fighting the gravity that the sun is itself dealing with. So it's presumably slowing up as it's maybe not accelerating. In fact, it's probably the other way. But at some point, you know, like a large planet, yeah, the particles will be captured by the planet because through the gravity of the planet. Yeah. If there's
Anybody else?
anybody else first?
Go
Okay.
on.
Okay.
Can you go down the curve of energy released by each fusion, like from hydrogen and helium?
Yeah.
To whatever they are. It's going lower and lower and lower. And eventually you get to a point where you don't have enough energy being released to trigger the next fusion. Is that, yeah, that's right?
Yeah, well, that's true. And so it's a little more complicated than that, but take the example of the sun producing helium. Okay, what happens is, so the hydrogen reaction stops all of a sudden. What happens? Gravity squeezes, and it will squeeze enough to get the temperature to that 200 million degrees Kelvin to cause the helium to create the next reaction. And that has to happen in each of the cases. Now, in the case of the sun and helium, it will not get to 600 degrees because there's not enough mass in the sun to get to 600 million degrees. So it carbon doesn't fuse. And it ends with carbon. But and the only reason that reaction ends at iron is simply because iron it becomes an endothermic reaction requiring squeezing hydrogen doesn't do anything for you. It creates a supernova is what it does. A mess. Yeah. Yeah.
I could get Stardust in our body.
Oh yeah, sure. Yeah. Yeah. Let's see. Let's go. Yeah. Yeah, this will be this talk will be on our website too.
We do have another question. I'm going to let you read this
Okay.
here,
Okay.
on my computer.
All right. What does dark energy, dark matter play in this grand picture? And could the angular momentum of everything in the universe be an explanation of dark energy? Okay. The answer is in the dark energy in particular is a large scale thing. Gravity overwhelms it, so that there's no effects of dark energy in our solar system, in our galaxy, even in nearby galaxies. You have to get 10 or 20 million light years away where gravity is weak enough that dark energy starts having an effect. So in our local environment, dark energy has no effect at all. is there, but it's weak. It's super weak. Gravity, when objects are close together, is strong, much stronger. So, like people ask the question, why aren't we, why aren't we flying apart? Why do we, that's a core question, by the way. Why do we exist? Why isn't the Earth exploding because of dark energy? Well, the answer is because gravity is way stronger. So, okay, but dark matter is another story. And in the scale of dark matter relatively, like in stars, I don't think plays a role in how stars behave, but it plays a major role in how galaxies behave on a larger scale. Because there's the amount of dark matter that would be present in a small cloud that would create a star is low enough that it's not going to be it won't be a factor.
All right, well, let's wrap it up there once again. Thanks, Mike.
Yeah.
That was covered a lot of ground there.
It did, didn't it? Yeah, yeah,
Time and space.
yeah, time and space.
Thank you very much.
Yeah, fair.
Thanks very much.
Yeah. There was a lot of